Hello everyone, welcome back to the new topic, that is Wellbore Effect. Till now we have seen in detail what is the transient well testing, particularly the build-up test analysis and drawdown test analysis. In build-up test analysis as well as in the drawdown test analysis, we had seen that there is a distortion in the transient well test data because of Wellbore effects in the early time region. So in this particular topic, we're gonna see detail what is this Wellbore effect or what is this Wellbore storage effect and why this create kind of distortion in the transient well test data. When we call transient well test data, it is the data for radial flow inside the reservoir, that is the porous media. If there is a deviation from this radial flow, then there will be some distortion in the transient well test data. So this Wellbore effects create some kind of distortion in the fluid flow geometry near to the wellbore, or because of the volume that is inside the wellbore, and that provide space for fluid to store. Because of that effect only, there is a distortion of well test data in the early time region. So in particular, when we talk Wellbore effects, it is of two types, that is afterflow effect and Wellbore storage. In general, when we talk Wellbore storage, it is including afterflow effects as well. But to understand the very minute aspect of this Wellbore effect, I am dividing this topic Wellbore effect into two, that is afterflow effect and Wellbore storage. So in afterflow effect, that happen generally during the build-up test analysis, and here you could see that like in a build-up test analysis, well was producing for long at constant production rate, and then well is certain for the build-up pressure, building the pressure inside the reservoir. So when well is certain here, right here, it takes some time to reach the production rate 0 at the sand phase. We are setting the well at the wellhead. In the build-up pressure, what happened that fluid is continuously producing. When suddenly close the well from the wellhead, what happened that fluid at the sand phase is still continuing to enter into the wellbore. This is the wellbore volume that provide space to fluid to enter inside the wellbore. So till the wellbore get filled completely, this Q at the subsurface will go to 0, but it takes some time to do this. So the time when we close the well at the wellhead, or the time when the flow rate at the sand phase goes to 0, this time period we call time of afterflow effect. So you understand only the wellbore volume that is there, it is providing space for fluid to enter even we close the well from the wellhead. Like this is the equation which we are using for build-up test analysis, particularly in this region. When this Q becomes 0 and pressure start building inside the reservoir because of transient effect, and that transient effect is inside the reservoir, and this is because of radial flow geometry effect that transient created inside the reservoir, and this equation is particular for that radial flow geometry, the pressure buildup inside the reservoir. Similarly, this Wellbore storage, this effect comes when we see the drawdown well testing. So here you could see that in drawdown well testing, the well was initially at certain condition for long, and then the well was put on production at constant rate. So similarly also we could see here until the subsurface production rate and the surface production rate become equal, That means whatever fluid is entering here, the same fluid, the same rate, the fluid is going out from the wellhead. It takes some time. This happens because of the wellbore fluid inside this wellbore. When we open the well from this wellhead, this fluid that is inside the wellbore, they come to this wellhead and went out of this wellhead first, and this is because of the compressibility effect or thermal effect, that fluid is residing inside this wellbore. So when it takes some time until when this surface rate becomes equal to the subsurface rate, and until this time we call the time of wellbore storage. And when this Q become, this surface rate and subsurface rate become equal, then we can apply this kind of equation that we were talking during the drawdown testing for estimating the pressure, wellbore flowing pressure in the wellbore. So you could connect this concept back to the previous lectures. I separated this topic because this is needed to understand, and it is one of the very important in well test design as well. So to calculate this time of afterflow effect, you utilize this formula, that is 1,70,000 into CS, that is wellbore storage coefficient. This is coefficient, not constant. Wellbore coefficient, and e की power 0.14 into skin divided by kh by mu. Here K and skin is the estimation from the Horner's plotting technique. Estimated permeability and skin. Here the wellbore storage coefficient is calculated by using this formula, that is QB by 24 into delta T by delta P. And this delta T by delta P is any point on this log plot, that is between delta P versus delta T. Delta T is certain time and delta P is the build-up pressure, the differential build-up pressure, that is PWS minus PWF. So we take any point on this straight line on a log plot, and corresponding delta P and delta T will be put back here to calculate the wellbore storage coefficient, and we could put back here to calculate the time of afterflow effect. Similarly, for in drawdown case, we apply this equation, 2 lakh plus 12,000 into skin, the whole bracket will be multiplied by the wellbore storage coefficient, and here the wellbore storage coefficient is calculated by this formula, that is 25.65 area of wellbore into density. One point here to note that every parameter here is in terms of field unit, like permeability is in terms of millidarcy, and H is in terms of feet, viscosity is in terms of centipoise, so area of wellbore in terms of feet square. So when we do the example, we will understand it better. So similarly, we plot this delta P versus delta T for this drawdown test as well, but here delta P will be the drawdown pressure, that is the initial pressure minus the wellbore flowing pressure, that is the after producing the well for certain time delta T. So when we do this log plot and choose any point on this straight line, and corresponding delta P and delta T could be put back to calculate this wellbore storage coefficient, and you could put back here to estimate the time of wellbore storage. But like in the previous slides, I talked about that when we start producing a well that is initially in the certain condition, it is the fluid stored inside the well that comes first, and it contributes into the production, and it takes some time to stabilize it. So this formula where the less time effect is there, that is CS into 25.65 area of wellbore divided by density, is more suitable to calculate the wellbore storage coefficient, and we apply this equation to calculate the time for which this storage effect will be distort transient well test data. So again I am talking this, when our afterflow effect will end, our ATR will end. But there is a assumption, there is a practical viewpoint that when this data deviation between log-log plot between delta p versus delta t, when there is a deviation from this straight line, unit slope line, at the point from where it is deviating, we go 1.5 cycle. After that, like it is disappearing at the point 1, so it will be like 50 hour when actually this afterflow effect will be ceasing to exist. So this is the normal hardness plotting technique, right? PWS versus log TP plus delta T divided by delta T. Here we can see there is a distortion in the data point in the early time region, and particularly the wellbore and near wellbore elements are responsible for this distortion. When we talk about in terms of time, that parameter will be influenced by the compressibility of the fluid that is residing inside the wellbore, or the wellbore volume, skin, and the thermal effect of that fluid that is inside the wellbore. And if you can reduce this wellbore effects in a larger extent by minimizing this wellbore volume. How can we minimize this wellbore volume? By installing PLT tool, that is called production logging tool, that will be lowering packer kind of system and will be setting and closing the well down at the near to the sand face. And this is how we'll be minimizing the wellbore volume. And then wellbore volume, when it is minimized in larger extent, we can reduce this effect of wellbore storage or wellbore afterflow effect, that combinedly we called it the wellbore effects, to distort this early time region data. Here you can see that there is a 2 point A and B in the early time region data. So sometimes this A and B is very wide or sometimes it is very narrow. This depends upon this wellbore volume. Larger the volume, larger the separation will be there. Smaller the volume, smaller this extent will be there. So generally when hydraulic fracturing is there, in the earlier video we had talked about the effective wellbore radius. So when hydraulic fracturing is there, that effective wellbore radius, the example we had talked for a, say, wellbore radius is 0.5 feet and the skin developed by this fracking is -7, and for that case your effective wellbore radius was around, I think, 1260. You can calculate back, you can see that video again. That was greater than 1000 feet. So up to that 1000 feet there will be a linear flow, and then after that 1000 feet there will be radial flow. In the initial of this lecture I talked about that whenever there is a deviation from this radial flow to other flow geometry like hemispherical or linear, you will not get the straight line, and this is because there is a distortion in data point in the early time region. So up to the radius up to which the fracturing has been done, until you test the well for certain time that your radius of investigation is away from that fracture zone, you will get the early time region distortion. For this, note that Ri must be, the radius of investigation must be greater than 1.15 into fracture half length. Or from this you can calculate back the time of wellbore storage or afterflow effect for a fractured well must be greater than 1265 μct fracture half length squared divided by K. This is a simple concept from the radial of investigation, that the time for well testing must be greater than this part to reduce the effect of early time region, or after that time only he will get the middle time region. So we talked all about this, what is this wellbore storage, and there is a mathematical background for it, and there is a constant storage model. Also there is a variable storage model that is very complex, and here only we will talk about only the constant storage model. So here QSF is the subsurface flow rate and Q is surface flow rate. We are talking again and again that when Q subsurface become equal to surface flow rate, then this Wellbore effect is ceasing to exist. So this model is explained like Q surface equal to Q surface subsurface plus QW, that is the accumulation term, either loading or unloading. Loading will be for during the drawdown testing, like when we're setting the well and fluid is still entering inside the wellbore, this is loading the fluid. Or during the drawdown testing, when we are opening the well at the wellhead, the wellbore fluid that contribute to the flow at the wellhead, that will be unloading rate. So this QW, that is accumulation term, could be written in terms of dimensionless term, that is Q subsurface divided by Q equal to minus 1 minus QW divided by Q. And QW, that is the accumulation term, in terms of, you could write C into dP by dt. dP by dt is the way fluid is entering inside the wellbore and they are increasing their height, and when increasing the height, that increasing the pressure derivative with time, and C the wellbore storage coefficient. So replacing back, you could write Q subsurface divided by Q equal to 1 minus C dimensionless into derivative of dimensionless pressure with respect to dimensionless time. From this equation, you could see that Q subsurface will be equal to the surface flow rate Q only when this right hand portion of this equation will tends to 0, and then you will get the surface flow rate equal to subsurface flow rate. Here CD is the dimensionless wellbore storage coefficient. The point is, this portion will goes to 0 only when this dimensionless wellbore storage coefficient will approach to 0. This comes into picture only during the log-log plot between delta P versus delta T, where deviation of this pressure data, differential pressure data from this unit slope line becomes parallel to the axis, and this will happen approximately 1.5 cycle from the unit slope line. We will talk about this. And from this understanding only, we calculate this time after which this Wellbore effect will cease to exist, and for drawdown test or injectivity test, we estimate this time using this formula. We talked about this earlier. Also for build-up test analysis and fallout test, we apply this equation, and time must be greater than 1,70,000 e power 0.14 skin into C, that is Wellbore storage coefficient, divided by either C or CS divided by KH by mu. So Ramis long back, they derived solution for this dimensionless pressure and TD, and they provided this Ramis solution. We call this one of the kind of type curve. So here you could see that different wellbore system changing different volume or different fluid skin, they plotted this chart. So this is one of the standard chart between dimensionless pressure versus dimensionless time. Here CSD is the dimensionless wellbore coefficient, wellbore storage coefficient, and CS is the wellbore storage coefficient. You could calculate either using this formula or either this formula. So what we do, we plot our actual transient well test data on a log-log plot between delta P versus delta T, and we superimpose our actual data from the field test over this standard plot, standard Ramis solution, and we try to match with the perfect plot, and selection of this perfect plot where this our actual plot is matching, it will give us the CSD value and the skin value. Let us see how we do this. So here, this is the one kind of Ramis solution and this is one actual pressure data that is plotted between delta P versus delta T, either flow time or either certain time. And what we do, we try to match over this standard Ramis solution, standard type curve. So we try to match our transient well test data over this, and wherever we get a perfect match, we say, I think this is getting closer, right? You got to see this. So let us see, this is almost matching over this type curve and our actual data, well test data. And from here we could conclude that for this particular well from which this data had been taken, the CSD value is 10 to the power 3, and for which skin is 5. And we could go further. This is type curve analysis, and derivative is for the future discussion. But I let you know that you could correlate it better. So we could also see here that this derivative curve could give you the better understanding about when this storage effect is ending. So this is the delta B versus delta T plot. This is the same plot, the unit slope line, and we plot derivative of this data. So what we could see that when this derivative is approaching a zero slope line, we see that radial flow is reaching, and before that the Wellbore storage effect is there, or Wellbore effect is there. So there is a deviation from this data point. Then we take the 1.5 cycle general thumb rule that was discussed before. Then we call, or we say that after which the Wellbore effect is ceasing, or after which the radial flow is dominating. Or we can say that our data will be actually giving the straight line in the hardness plot line. So I hope that you understand it. What I wanted to tell you, that if you had any doubt or any question in your mind, any suggestion, you can write back to me, or you can comment it in the down comment box. Thank you for the discussion.